Probably I have a profile which is quite original to a number of you, since I am at the same time a roboticist and a cognitive scientist. And I run a lab which everyday research activity at Inria, which is a research institute in France, is basically trying to study and model the mechanisms of learning and development in children, but through the use of algorithmic and robotic models. So I'll give you a little glimpse of what it can look like. For example, trying to understand how curiosity-driven learning can work. But that's not the main topic of my talk today. Today I'm rather going to talk about another dimension of what we do, which is trying to understand what can be the application of such robotic models and tools in the domain of education. And so first of all, I'd like to highlight one great educational challenge related to the digital revolution. So today, ICT systems are part of our everyday life, and they are doing something quite extraordinary. They are extending our mind, they are transforming our social relationships, our professional lives. And in particular, if you look, for example, at the example of search engines and information systems, they are basically working with algorithms that are automatically filtering in and out information, which has a huge impact on the way we learn and understand the world around us. And of course, it can be a great opportunity, but only a great opportunity if you can understand how it is working and if you can understand how to leverage the logics of these algorithms. And the only way you can really leverage the logics of these algorithms, which are impacting your everyday life, your mental life, and your social relationships, is by having some basic understanding of algorithms themselves. And this is why today there are a lot of actions trying to introduce the teaching of basic computer science principle at school. It's a bit like music, you know? Music is something that many people have an intuitive understanding, but not so deep. If you want to have really a deep understanding of music, you need to understand the rules of music, how to read notes. It's not always so funny. The same is for teaching computer science. How to teach that in a way that is enlightening, but also motivating. And robots can be actually a tool, a context which makes learning computer science motivating. But it can be further than this. Actually, today we don't have only a digital revolution, we also have a revolution where ICT systems are not only connected to each other through digital connections, they are now embedded in everyday physical objects. And it happens that those physical objects are more and more becoming robots. So when you talk about robots and the future, you usually think about something that's going to be very important indeed, like robots in the home that they help you in your daily task, whether you're handicapped or not, whether you're young or elderly, like, for example, the robots on those photos. But actually, there are many robots that are already in our homes. We don't call them robots, but they are robots. These are for example, the sensors, the systems you put in your home that detect the weather and change the heater system of your house, or the connection between the cars. Cars are today robots because they are embedded with sensors and a computer which take a lot of decision instead of you to help you drive your car, and it can save you your life, or it can put you into danger. And it is connected to many of the devices. And so this is really a revolution coming in, which is going to be even further than the digital revolution, because those don't only extend our minds, but they at the same time extend our minds and our body. And so it is very important also that everyone, and children in particular, come to understand the logics of this robotic and Internet of Objects revolutions. And then there is a last aspect of the robotic revolution, which makes that it is quite important to understand this new world, is that robots and computer science are not anymore only tools to help us in practical everyday tasks. They are becoming to be tools to think and understand ourselves. So in science, there is a big revolution in the last decades, where robots and robotic models have been used to understand some of the mysteries of humans. So for example, for those of you who were already at the talk of Luke Steels 2 hours ago, one of the great things that you've been doing with this group is trying to understand how languages form. What is the origins of languages like German, French, Japanese? How do they form? There is no chief of the language which imposes the conventions for which lexicon are we going to use, which grammatical rules. This has been a mystery until quite recently, where experiments have been made by having population of robots with models of mechanisms of language acquisition and transmission, and understanding how languages can self-organize in a group, a bit like the fantastic architectures of termite nests are not the result of intelligent termite designers, but the interaction of all the termites. Another kind of examples is, for example, the role of curiosity and spontaneous exploration in children. It seems to be really important for their cognitive development. But quite until recently, we did not really understand the mechanisms of curiosity. And some of the experiments we've been running, for example, in my lab, have been manipulating algorithmic models of active exploration and active learning, where those robots, for example, that are here, they are embedded with models of how an organism can discover its world, a bit like a little scientist. It's making experiments, making movements, observing the effects of those movements, collecting the data, and then trying to learn the regularities, and trying to interact with some objects which in the beginning they don't know, they don't react, like this object, and later on interact with social peers which do react. And basically, with those models, we've generated new hypotheses about how curiosity can automatically organize development across the time. Something that's mysterious in child learning is that they follow some particular curriculum of development. They don't learn, for example, how to walk with two legs directly. There is a whole sequence of developmental stages where they learn how to flip on the belly, how to sit, how to walk on four legs. And then, with some of these active mechanisms that we discovered and enlightened with those robotic experiments, we proposed some new hypotheses. And basically, it also allowed to underline the fundamental role of curiosity and social learning in development. And as you will see, robots can promote that in classrooms. So let's go now to some educational robotics projects that are the application sides of some of this research, and that are related to the educational challenges I mentioned. I'm going to describe two projects, one which is called Inria, which is about teaching robotics and computer science at primary school, and another one which is called Poppy Education, which is about teaching computer science, robotics, and digital fabrication and the world of makers to high school level universities. And for each of them, I will quickly present several components. First of all, as you'll see, there is technology, but these projects are not technology-centered. They are really pedagogically centered. So one of the things they contain is really pedagogical contents with a set of activities that you can run in classroom and outside classrooms associated to open hardware and software. Openness is also a key of those projects, since everything that I will present are examples of a larger project where everything can be found online and freely. And those kits, they are always done in very close collaboration with teachers, which is something obvious as a methodological tool, but which is really a challenge from a certain perspectives. Then I will present examples of experimentations of how those tools can be used in various educational contexts, inside school, but also outside schools, and how evaluation can be done. And then I'll very quickly discuss some challenges that arise when you think about how to scale up those experiments to the whole educational system. So first of all, before presenting the Inria system, just a link to the fact that those kind of projects takes inspiration from a number of pioneers, especially, for example, Seymour Papert, which pioneers, especially in the US during the 60s, the concept of constructionism, where the fact of acting with the hands on concrete and physical objects is key to learning for infants and adults, and is, by the way, something that is today lacking importantly in online education tools like MOOCs, as well as the social interaction, which is key. And so Papert developed a number of robotic prototypes for education in the 60s, and we are taking the follow-up of that. So the Inria Robot project is a robot project that has been targeting primary school level, 6 to 12 years old. Actually, in school and outside school, so in France, it's not the case in all countries, but in France, after the school, every day there are activities in the buildings of the school, but not by school teachers, by the animators from all domains, and this is called periscolar activities, and you have a lot of freedom for activities here. And those activities typically target groups, classroom, but classroom where kids don't work alone, they work by groups of 3 typically, and typically the kind of experiments that we've been doing about that is, in general, 10 sessions of 45 to 60 minutes. And so, first of all, what are the pedagogical objectives of such a project? So first, there is a disciplinary goal. The disciplinary goal is basically to teach the basics of the conceptual foundation of computer science and robotics, and related to that, teaching also the societal dimensions of those technologies, like leading the kids to think about what can be the impact of having such technologies in everyday life. And then there is also interdisciplinary goals, which is one, take this context as a tool for learning the scientific methods, and 2, learn how to work in groups. This can be done with other tools than robotics, but robotics is especially useful in that concern. And then the strategy is that first, robotics provide a motivating context. It provides a micro world where learning the connection between computer programming, the digital world, and the physical world is particularly obvious. Then we are using an inquiry-based method. In all the activities we develop, the teacher never first explains the concept to the children. The children are always given a challenge or a question, and they need to find the answer by themselves. And last thing, we try to use cheap and easy to use hardware and content, in the sense that something that's easy to use in real classrooms, given sometimes the technological and administrative limitations that characterize at least French schools. I don't know how it is in some other countries. So here the hardware we use was developed by EPFL in Lausanne. It's a very small white robot, and it's associated with software tools that allow visual programming with no text at all, which means that children who don't know how to read can learn how to program. And the first step to design those activities, which is always when we do that, is that we first design a conceptual map. What is the set of concepts that we try to target in those activities? And we've been building this, so don't read the details. It's not the idea of reading the details, but it's just to mention that before developing the practical tools, we really have a fundamental thinking about what are the main concepts and what are the priorities we want to teach. For example, one of the important things with robot and programming is allowing children to understand not only what is the concept of a language, of an instruction, but also the fact that to solve a problem, you can make a program without knowing all the details of the particular program in advance. I will give you an example quickly, in an example of activities. So what kind of activities do we use? So first of all, something that's quite representative of the method. The first day, typically in the activities, the children meet the robots. The teachers or the animators never use the word robots. They are asked not to use it. They come into the classroom and they say, okay, today we are going to do an activity with these little things, which a friend of mine gave to me. We have to discover what it is. And he gives it to the children. And the children are left alone for 10, 15 minutes. And then questions. And so progressively they are brought to understand what are the reactions of this thing, that sometimes this thing does things when you push on buttons or when you push things in front of them. And progressively they build the concept of a robot, not from the movies they have seen in the cinema, but by their own experience. And the word robot is bring in the classroom at the end of the course. Another kind of activity is, for example, a bit later, that they have to find the solution of how to go out of a labyrinth. And typically, here, this is where they learn the concept that you can have a very simple program that allows a robot to go out of a labyrinth without knowing the shape of the labyrinth before. Okay. And with such kind of activities, basically, we try also to make evaluations. And I won't enter into the details because I want to present in more detail the other experiments. But the kind of thing that's interesting as a preliminary result is that it seems that not only all ages can take advantage and understand the important concept of computer science, but it seems that girls get even more than boys out of those robotic kits. And the last word on this project is how is this scaling up today? So initially, such a project was really made with very little resources. Typically, 2 researchers, 1 or 2 students, working with teachers for a few months. And then after this, it has begun to disseminate in a number of towns in France. And now there are 35 towns in France using the kit. And basically 7,000 children have been using it actually in less than 1 year since the release of the kit, which is openly available on the web. Of course, the robots, you need to buy them because they are hardware, but you could actually build them if you want, because everything is on the web. And something that's key in that is that we don't only provide just ideas of activities and the hardware, but a concrete road book which makes that the teacher exactly know what to do by reading the book in the classrooms. And actually also, the way they train themselves is just by doing the activities themselves. So the activities are made in such a way that when you do them, you know how to do them to children after. Okay, let's go to the other project, Poppy Education. So Poppy Education now is rather targeting higher level classrooms, and basically it is extending the target of teaching the computer science and robotics concept to something that's even a bit larger, which is the maker's revolution. That today we have a number of technologies that allow digital fabrication, very fast prototyping by mixing things like 3D printing and fast electronic prototyping like Arduino or Raspberry Pi. And basically what you need to teach, it is opening, which is new, is that these are not only tools for programming everyday things, but tools that allow us to multiply the capacity of invention. And so it is a way to teach how to invent new hardware. And again, here there is the dimension of teaching the societal dimensions, especially brought by applications in the domain of human-robot interactions. And so in this domain, we've not reused an existing kit. We have actually developed a new one based on 3D printing. And we've actually developed the first worldwide 3D printing open source humanoid robot that you're going to take a look right now. So this robot is called Poppy Humanoid. And actually, interestingly, at the beginning, it was not made for education. It was made because we wanted, for the scientific part of our activities, to understand how the shape of the body, the geometry, the distribution of mass, can have an influence on the acquisition of skills like locomotion, or also on social development. And so we needed to have a robot where we can very easily change the shape. In one afternoon, we can make a new drawing, print it, assemble it, and test it. And very quickly, as we made that very modular and quite cheap and open source, we realized that it also matched the needs of education. And so all the white parts that you see here, they are 3D printed. And because this robot is modular, I'm going to show very quickly after this video that instead of the fact that here you see a humanoid robot is only one of the different shapes that you can do with the Poppy tools. So I'm going to show you in 1 minute. Okay, and so with these building blocks, which are basically hardware and software building blocks, you can invent robots with many different shapes. So for example here, you see a robot which might look like a bit, you know the Luxo Junior thing in the beginning of the Pixar movies? Well, here it is. Here, this is a flying poppy made the 1st of April. So it was a bunch of students on the beginning of the morning of the French of April. They say, what if we want to make Poppy fly? They made a drawing, they printed it, beginning of the afternoon, they assembled it, middle of the afternoon, they shooted the movie. Okay, and since we are in Bordeaux, of course, a little a little funny thing, but just to illustrate how you can open the system and transform it, because this system was meant to be really hackable. So here is a little robot that actually mixes the robot that was made by EPFL in Lausanne with the little Luxo Junior robot that you just saw. And this was also done in just 2 days. Okay, so that was just to the... And now, with what kind of tool can you program those things? Again, we are working on tools which allow even the beginners, those who never touch a computer of their life, to quickly discover and learn how to program those robots. So basically the tool that we are using here is the Scratch programming environment, which I'm sure many of you know, which was made initially to allow primary school children to learn how to program. But actually there are variations of Scratch, such as one called Snap, which extends the possibility of Snap such that it keeps the visual simplicity. You don't need to learn the complicated syntax, but you can program you can make programs of any complexity that you want. Like, it's as powerful as any other programming language. And for example, this visual learning program is not only used in primary schools, it's used in high schools, it's used at university to teach computer science. So you might ask also how much does it cost if you want to build such a robot? You can do it in your garage or in your school if you have a 3D printer, and if you do that, probably it will cost you around between 100 and 150 euros. And if you want to buy it by a simple click on the internet, you go to our website, and I think in 1 or 2 months you can get it for around 200 euros. So what we try to do is having robotic systems which are not too expensive also to enable their actual usability. Okay, let's go to what comes after. Something that's also important, I said, one of the very practical challenges that we have when we need to develop tools, to develop activities in schools, is that we don't want to have schools install softwares on their computers. In France, when you ask teachers to install software on their computers, it stops because they don't have the admin access. So how do? We develop robots which come with a Raspberry Pi in the head, or hidden somewhere, and this Raspberry Pi has a web server, and if you want to program the robot, you just open a browser on your computer or even on your cell phone. You give the internet address of the robot, and that's it. You can directly run, for example, Python in the browser, or the visual learning tool that you saw just before. So no installation. This seems to be a simple thing, but in the schools, to us, it has opened many doors. So example of an experiment in a high school, which is a high school in Bordeaux, which is training young people for manual jobs, like young people who will become plumbers or electricians. And we've been developing a project which is mixing science and art learning activities. And the way these children have been introduced with the technology is not by the technology, it is by art. Actually, we've been working with artists who did build a scientist residence inside a high school, and they invited the high school students to help them build the artistic piece. I'm going to show you the video of the result of this piece just after that. And during this, the artists, for example, they explored questions with the students such as how movements generated by a machine can transmit emotion, how a machine can simulate living or can obviously show it is a machine through its movements. So this kind of thing. And then, after the artistic works, the technology, the robots come into the classroom, and then we build groups, several groups of students. And then some of them, for example, have been working with inventing a new 3D design for the robot. Here you can see on the left a wheeled platform that was invented by the children. Other groups, they've been working on programming and mathematics. So those high school students, they are not very motivated by mathematics in general. With programming, they had to program some kind of funny movement with the robots. And doing things like this, how do you do that? You use a sinus. Sinus is not the typical thing those children like to work with. But in this context, they came to say us, oh, we understand what is the whole purpose of a sinus at last. And then, interestingly, all the groups work with electricity and physics, for example, making a battery for the robot. And this was interesting because not only it changed the way the students relate to the teachers in the schools, because actually the teachers in the schools, they were not so much expert with those robots. They started at the same level than the children, and their expertise jointly increased together, and this was very motivated for the children. And among the teachers, it created links between teachers who were specialists in different disciplines. So the physics teacher talked with the mathematics teachers, who talked with the philosophy teachers. So this is the little video showing the result of the work they did with the artists. Okay, last two very quick examples. We do not only try to experiment how those tools can be used inside school, but also outside schools. For example, in the fab labs that are targeted to teaching digital fabrication to every citizens, the young, the less young, the experts, the beginners, everyone. And for example, there are recently 6 science museums in France who jointly built a project with us where they have been organizing workshops where citizens could come to assemble such 3D printed robots, could participate in debates trying to understand the societal implication of those robots and cultural activities, inventing pieces of art, pieces of theater, for example, based on the technologies. And quickly a video of what it looks like to implement a workshop in such places. You will see a lot of tinkering and a lot of other objects that were not made by us, but which tinkering naturally comes. So here this is, for example, quickly the use of a makey kit, where you learn how to make an interface with the robot using fruits. You touch the fruits and it makes the robot moves. And the last thing is the last project I wanted to talk about, is those robots, they are not only used in the context of teaching technology-related things. They are actually also used in artistic classes. For example, here, a number of dance teachers are using the robots to teach dance to very young children, as well as to university students in art. And quite interestingly, why they use the robot is that this is a tool that's extremely interesting to explain the structure of movement, the structure of the body, how movement is generated. And basically, when they come into the classroom with the kids, for example, with the robot, they use the robot as a tool to explain what is below the flesh of their body, how they generate movements. They ask the children to produce a movement with the robot and then to reproduce it with their own body. What are the similarities? What are the differences? And what's interesting is that not only it is motivating for those dancers to learn dance, but doing that, they are progressively acquiring a number of technological concepts. And what we found out is that after a few days of using that robot, at the end, those little girls that you see here, at the end, they are actually understanding most of the major computer science concepts that we initially targeted and I described earlier in my big conceptual graph. And so this is a very promising way also to explore these targets. And I'll finish here. If you want to know a little bit more or discuss, there is a forum with more than 700 members from all disciplines, educators, artists, engineers. So come discuss. Thank you.